All right. So far in instrumentation, we've talked about resistors and we're starting to talk about what's known as analog circuit components. And kind of to show you where that's going, I'm going to do what I do best, which is take things apart and break things and maybe not so much put them back together. And so I've done that over the years and kind of have a collection of things. And I want to show you some real components and real devices that maybe you recognize. And so the first one is potentiometer. I don't know why this is having so much trouble focusing, but all a potentiometer is an adjustable resistor. And so this would be like a volume knob where you would turn the knob and basically the resistance would change. There's a couple ways you can lay that out. It could be, well, first off, think about your resistor. This is your symbol for a resistor. Potentiometer just has an arrow going through it like that. And in fact, anytime you see an arrow going through a component, normally means it's an adjustable component. So in this case, this is an adjustable capacitor versus regular capacitor, or adjustable inductor. That's sometimes called a slug versus a regular inductor. We'll talk about capacitors and inductors later. Just for completeness, put a resistor up there. Anyway, and mechanically, the way this looks is I'm going to have to draw a coil in a circle, and it's not going to work out real well. Anyway, basically have one terminal at each of the ends of the resistor there, and then there's this piece called a wiper attached to the knob. And so basically your resistance is changing here. It's technically changing here, but whatever. And as you turn this knob, the resistance, basically this wiper drags across here and changes the resistance. So it's really good for tuning things. It's really good for adjusting things. So you'll see these in real life periodically. Sometimes good to just for adjusting things, like sometimes you'll see on pieces of equipment it'll say trim. A lot of times that's a potentiometer, and you're just trimming some to tune something. So that's what that's about. So I'll try zooming in there. Maybe that'll help focus. Okay. So that was that one. Let's see, what else do I have here? This is a cell phone charger for a car. And so a couple components here. You probably recognize the LED. Probably recognize the little USB part for plugging in your phone. There is, instead of a LED, there's a regular diode right here, and you can see there's a little gray stripe, and that corresponds to that part of the diode. And you got a couple capacitors on here as well. These big circular things are electrolytic capacitors. We'll talk about those later on. Big thing I want you to notice with these, though, is there's no way I'm going to get to focus on this, but if you look really carefully, you can see that there are negatives on them. And if you look really carefully, you can see there's positives on some of them. While resistors didn't care which way you put them in, and disc capacitors like that right there, a little ceramic piece, don't care which way they go in, these electrolytic capacitors have a polarity, and you have to keep track of that. Got a resistor there. You probably recognize the resistor. There's a little integrated circuit. We'll deal with those starting next week. And then this spring is actually part of a fuse. And so schematically, a fuse just looks like that. And in reality, what it is it's a tube with a piece of metal in there of a known thickness and everything. The idea being, if this metal heats up too much, it'll melt and break the circuit. So suppose you had your car battery. Suppose this is your cell phone charger. And we're just going to call it RL. It just means load resistance. This is 12 volts, and it's, car battery, maybe you're capable of delivering 600 amps. Doesn't mean you're running 600 amps all the time, but it's capable of it. Now, suppose I were to shove a penny in here, I'm a little kid and I shove a penny in the USB spot. Well, really what that does is that. So now I have 12 volts. Maybe the resistance of that penny is something like that. So if we look at what current flows through there, 12 volts, you can see that I is very big. Now when we think about running high currents, that's how we often, that's a good way to get a fire, is having lots of current. So instead of allowing that to happen, what we do is we put a fuse in here. And on schematics, you'll sometimes see it written something like that, where it's got some current value listed. The idea being, this fuse will break after 10 amps. That'll open up this circuit, and even though this part's shorted, you won't have that high current because there won't be a current path. So that's how, you'll hear people talk about short circuits, you'll hear people talk about broken circuits and stuff like that. Really what's happening is, if we break a circuit, we call it an open circuit. If we bypass our load with some other thing, that's called a short circuit. So in general, anytime you're doing anything from a power source, you want to put fuses in to keep it from burning up before, to have too much, in case there is something that's shorted out. Okay, so that's what I wanted to say about that part. Let's see, what else have we got? I got plenty of things still right on here. Okay, so another component here is graphing calculator. You may not recognize it, but there it is. Graphing calculator, what's left of it. Got all these buttons, right, that you would press. And I'm not 100% sure, but I think these are probably capacitive, so that when you press the button, there's basically a voltage spike from a capacitance change, and we'll talk about capacitance later on. But as we do that, that's what registers it. And, that registers that button was pressed. Now, if we flip it over, a couple things to notice here. You can see some of these things have C, some of them have U's, just a circuit, but there's R's and L's for inductor. Say L3 be for an inductor, power jack, and the C12 would be some sort of capacitor. And also notice that none of these components go through to the other side. So unlike the stuff you're building on your breadboard, these things are all kind of just mounted on one surface, and that's called a surface mount. And so the way this is soldered, I know this is a question on the first homework there, was they basically put down little pieces of solder paste, and it's like paste like you would eat in elementary school. And then a machine lays out all these components on here, all these little resistors and such. Then you take the whole board and you blast it with some hot air, which is just hot enough to melt all the solder paste. And basically, when it melts, that allows the chips to settle and all the little components to settle. Then it goes off and gets cooled, and that's how nobody's sitting here with a soldering iron soldering every single one of these at this like really narrow pitch like this. Okay, I think that's most of what I wanted to show you on here. Don't see anything else. We'll point out, so you've got this display here, and if you've used a graphing calculator, there's lots of things you can put on that display. And notice there's only a couple wires going there. So if you think about all the little pixels that are on here, and that there's only that many wires, there has to be some processing that's happening to determine what goes through these wires at what time, and what on this end, how to handle that. And so we'll talk a little bit about that. But that means this display actually has to just constantly update, and it's just going through, and it has to do it fast enough that your eye doesn't notice the difference. So we'll talk about that when we talk about sampling later on. I'll deal with that one in a minute. You're not the star of the show yet. You sit over there. Okay. I've got some electric motors, and inside of here, No way I'm going to be able to focus on it, of course, but there is some coils of wire and some permanent magnets. And so the idea being, this is a little DC motor. We apply a voltage to it that generates a magnetic field and basically turns. So basically we generate a magnetic field in there. The wire wants to turn, or the coil wire causes it to move, to the other magnet, and that's what gives it the spin that we want. If we throw a little weight on the end of it, so I don't know if you can see it, but there's a little tiny motor, but it's got a little offset weight. We like motors to spin and not vibrate. The reality is they do a little bit anyway. In fact, one of the things you can do for equipment monitoring is measure the vibration. And when you start to see the vibration getting stronger and stronger, you know that maybe you've got bearings bad, or you've got to clean it, or something like that, so you can maybe fix something before it fails catastrophically. A little instrumentation problem. But in this case, we've intentionally added a weight to the end, and you can see that there's like this little weight. This is actually for your cell phone. So somewhere in your cell phone, if you set the phone to vibrate, that's what's happening, is we send a little signal to this motor, and it spins, and this little weight flops around, and that's what causes your phone to vibrate. Same electric motor. This one I can't turn by hand like I could with the others. The reason is we've got this whole little transmission here that basically slows down the speed, but then increases the torque on it. And so this motor was actually for billboards. So you'd have a whole line of these, and you'd have some sort of flat piece that would have a sign on one side. Then periodically there'd be a signal sent to these motors, and they'd all turn, and you could see the other side of it. So that's what that's about. Okay, so I did that. For 10,000 points, you'll probably never guess what that was too. And what this was part of a regular phone back when phones lived on the wall and not on the not in your pocket. So when you hang up the phone, that's what this big switch was. Click, hang it up. Got all these little connectors, and you can see the wires coming off the connectors there. So there's your little phone connectors. There's a good example of a fuse right there. There's a fuse. You can see there's a little glass tube with a wire in it. It's not going to focus on the wire, but it's in there. And we got all sorts of little resistors. You already learned about those. These little devices are transistors, and it's going to be hard to see, but they have 3 pins. Flip it over, maybe. No, that's not going to help. Anyway, they have 3 pins. And we're not going to spend a lot of time talking about them, just because if you want to learn a lot about those, you take an electronics class, or like a real electronics class versus mine. And yeah, there you can see the 3 pins on that one. And but they basically can act like switches. They can act like amplifiers. They have a bunch of different purposes. And these are really, really big transistors. Your computer has millions of these in it. Let's see, what else do I need to point out here? A couple diodes. Some of these straight wires are just jumpers between things. And some more electrolytic capacitors. Anyway, so some of these filters are probably doing, or some of these capacitors are probably doing filtering. This is probably a big inductor for filtering, basically to clean up your voice signal when it comes through. So yeah, that's what, and it does have a couple integrated circuits on it. You can see those. And let's see, I think that's all I really needed to show. It says ROH. This actually isn't a super old phone, because if you look, that says ROHS. And I forget what that stands for off the top of my head, but it's basically, you'll see things listed as ROHS compliant, and that means that environmentally they are friendlier than other components. And so places like Europe require you to use ROHS compliant components. So that was cool. Took open the phone, saw that part, and I said, I wonder what's in the handset. And the handset, right? Like, that part. And I did everything in my power to break this thing. I threw it off the balcony there between Jones and Jones Annex. I did all sorts of stuff and couldn't get it broke open. Finally, I put the thing in a vise and tightened it down and cracked open the pieces. Probably, I don't know offhand, it may have been, sometimes you can ultrasonically seal these. Anyway, finally broke it open, and then it wasn't very satisfying to look inside. There wasn't much. And what there is there's a speaker and a microphone, and that's it. And interestingly enough, the schematic symbols for these: speaker and microphone, they're pretty much the same. And if we think about how a speaker works, you'll see why. All a speaker is you got a magnet, paper cone. You can get plastic cones too if you don't like nice things. And then there's basically a big coil wire. And if we send some signal through here at some frequency, somebody singing or playing guitar or whatever, as that frequency changes, the magnetic field's going to change, and that's going to cause this whole cone to move back and forth. And that's what's generating your sound, because it's moving at some frequency, and that's the frequency we hear. So really kind of a simple device. Our microphone, and I'll make it face the other direction, we speak into it at some set of frequencies. That causes the cone to move, which causes the magnet to move, and we generate a current. That current comes in, and based on what resistor we have here or whatever, we have some voltage. And so basically it's just the same thing in reverse. And in fact, at least one New Jersey mafia guy got caught because when the FBI went to set up bugs in his house, the wiretaps to listen to him, he had some high-end stereo equipment in the 80s, and they just went in and they had this big old speaker and basically used that as a microphone, because the same sort of thing was happening. He would have his conversations, and they weren't really listening to music when that would happen. So he just had this big set of speakers in the corner, and as they talked, it picked it up. His voice would cause this to move, would generate the current, and then instead of there being this V here, there was a little transmitter. And so basically, the FBI could sit outside and listen to everything he was saying. So that's literally, these are just the same thing, the speaker and the microphone. In fact, you can use a speaker as a microphone, as I just demonstrated. So that was the handset. I also wanted to, just as kind of the last piece for this lecture, this is a kind of a big device, and you see a symbol here. This is a 480 volt 3-phase line. And if you think about when you switch on a light switch, you walk into a dark room, switch on a light switch. You see, if you're looking at the light switch, you might just see just a little spark. Basically, as you close that switch, you can get a little arc. But as the switch gets close to being closed, you get this little arc across there. And for your light switch in the house, it's probably not that big a deal. But if you start using higher voltage stuff like this 480 volt line, and in industrial settings where you might go to 11,000 volts or something like that, that little spark starts to be a bigger and bigger deal. And so there's whole training courses on how to deal with this. It's called arc flash. There's in your house, if you trip a breaker, you can just walk over it. You just check to make sure it's safe, make sure somebody's not being electrocuted or whatever. But you can go press the breaker and have it reset. In an industrial setting with higher voltage, you may not do that. You may not just walk over to the box. You may have a tool that you stand a long ways away, like a big fiberglass broomstick, that you poke it, and because of this arc flash. So at 480 volts, maybe this goes to whatever piece of equipment I have, and this goes to the power supply, or vice versa. Rather than just walking over and unplugging it, where I risk being showered in sparks from this arc flash, instead I press this button. See, it says off. That's nice to know. Give it a twist. And so the idea is that connection gets broke inside of here, so all the sparks and molten metal and everything else that happens gets sprayed inside of here versus on me. now they're disconnected and I can just pull them apart without that risk. So there's all sorts of little devices like this. If you work in industry, you'll start to see this sort of stuff. Anyway, it's a pain to get back together, so and I won't embarrass myself here on the video trying to push it together under the camera. Anyway, so there's some just general components. I want you to just think about that in your regular life, like looking at devices and what might be in them. So all right, other than that, I'll have a couple more videos for you here later.